how we can cover the concepts to begin with. Then we gradually get into the inside of MapReduce itself, and from there take it down to the hands-on and execution models and internals of Hadoop itself, and how the whole thing works. And then eventually we'll get into the data types and other things associated with it. So the key thing is to understand the concept. So MapReduce has been there forever, but to understand the concept is something which is very, very important as we go through. Apart from the concept, see, there is one more thing which has a practical usage when it comes to where people have to really struggle around. Given a problem statement, what is the best way to make it more distributed on the platform? So let's say if you are looking at Hadoop as a platform, and if you want to make it distributed, what are your options? So fundamentally, the option is only one at the root level of it, which is MapReduce. On top of it, you have multiple options, which is like the Hive or Pig or do multiple other things which you could do to make it parallel and distributed. But at the core of it, it's still MapReduce. So that's the very important why MapReduce becomes so powerful for you, because once you get into an area where you cannot really solve the things by Pig or Hive, or it becomes a performance issue, you really get into trenches and start writing in MapReduce. But with that said, it's not like every time you get into MapReduce and start writing MapReduce. You would write MapReduce when you really need it. Otherwise, you still want to keep it more simple, maybe a SQL-like construct in Hive, or more of a scripting style in Pig. So that's the construct. I think Pig and Hive will get covered as we go through. But the fundamentals here is how MapReduce is different. So before we start, there is one more thing which I want everybody to start relating. Is when we started the whole programming, maybe 20-25 years back, the whole system was we used to have lower level programming, and the programming actually matured over the period of time to get to the fourth generation and fifth generation languages. So what we saw is if you want to draw parallels to that, if you say that something above an assembly level, if you have to code, that's precisely what you would do it in MapReduce. You pretty much have very powerful capability. You can do almost everything which the Hadoop system offers through MapReduce. While as we go up the layer, the controls becomes a little more tighter, and the flexibility becomes a lesser. But we are looking at a raw performance and making it more powerful. Yeah, MapReduce is the way to go. So this is sets the context on what MapReduce is all about. While we go ahead and look at the details. Coming to what fundamentally MapReduce is all about. So the origination started from what we call as the functional programming model. But before that, let's look at it. What essentially MapReduce is? Is it a language? Is it a style of writing code or anything? Fundamentally, it is just a programming construct. It's a programming model, and a programming model which helps you program on a larger set of data. So that's the key construct of MapReduce. What MapReduce is giving you is a programming style or a programming model which helps you to conquer or compute on a larger data sets. So how does it do? Yeah, we'll come to that. But that's the key message which we need to remember, that MapReduce is not a language. It's a programming model, and it helps you. It gives you a construct on how to program into Hadoop. So that's the key aspects which you need to remember. So the thing is, it becomes very difficult to do programming on a distributed computing infrastructure, and there are a lot of challenges with distributed computing infrastructure. And one aspect which MapReduce is trying to do is to simplify that whole process. Okay, so we look at how it simplifies what are the challenges with distributed computing, and things like that, and then we will come back how MapReduce really helps you do that. So from a academic perspective, so the whole thing is inspired from map and reduce functions which are there in the functional programming construct. So folks who know the functional programming, so it's basically saying that you have a function. The function takes in some data and gives out some output. So anytime you call a function with a certain input, it always gives the same output if the data remains the same. So that's the functional programming construct, where the functional programming doesn't really depend on the state of the data which is available within the system itself. So it's always dependent on the input data. So you give 1 and 2, and if it is giving 5, next time you give 1 and 2 to the function, it will always give 5. It will never decide that, yeah, you have computed it earlier, so the number was 3 and now it will be added 3 to another thing and give a number. So it doesn't preserve the state. So that's one thing which we need to remember, that MapReduce functions are state independent. And then you will say that, yeah, we need to find sometimes the state and things like that. We will come back to that. But the whole thing is, when you are looking at functional programmings are usually state independent. You give an input and you get an output. And when you get the output is always a function of input. And anytime you give it, it always gives the same result. So in the functional programming, there are many constructs, and one of the constructs is map and reduce, and the whole idea has been taken from there, and the whole MapReduce concept has come through. Google first implemented it in for the distributed computing. Before that also it was used in some certain languages, but the whole idea came into prominence after Google published the papers on the distributed infrastructures. So both for MapReduce and the distributed file system. So once they published it, yeah, people really understood that, yeah, it is this paradigm which will help us conquer the distributed world, and hence it started in that direction. So to summarize, key things to remember. One thing, which MapReduce is not a language. MapReduce is a programming model. So which essentially means you can program in almost any language. You can take any language and you should be able to program in MapReduce. So that's the first thing. Second thing, it's state independent. So it's not dependent on any of the internal state. The key construct is based on the input data you give it. Based on the input data, it will give an output. So that's the two things which you need to really remember here. And one of the other thing which we look at from a distributed computing is that how do you bring in scalability? When you are getting larger and larger data, how can you make it more and more linearly scalable? And to do linearly scalable, one of the things is you really cannot rely that somebody will store a state, he will pass the state to somebody else in the network, and then the whole computations will work. So you need to have a system which is pretty stateless, so that you can start up another node, give it some data, and it will process and give you an output without worrying what data somebody else in the neighbor has processed it. So that's what it makes, the stateless nature makes it scalable. So to emphasize that, let's say we have 10 clusters, 10 machine, 10 nodes which we are looking at, and each node is processing a data output. The key programming thing which you are looking at is each of them doesn't talk to each other. If they talk to each other, that means they are talking to each other for exchanging states and other things. And when the moment you start talking to each other to exchange the states, the system is not that scalable. It's not very largely scalable. Yeah, I don't say that it's never going to be scalable. Yeah, there is challenges around it, but fundamentally, if you eliminate the discussion between the nodes, that itself is a big achievement, and that's the first stepping stone for scalability. So these is the three things which you need to remember here. So let me move on to the next one, where we look at the key features of a MapReduce system. First, I introduce MapReduce. Now, there is a difference between MapReduce and a MapReduce system itself. So that's another key differentiation which we need to look at. So what's the difference between a MapReduce and a MapReduce system? So MapReduce, as we said, it's a programming model where it consists of two things, map and reduce function. It is pretty stateless, where it takes the data, gives the output. And it makes it more linearly scalable because none of the jobs will talk to each other, because it only depends on the data which it gets, and it will give an output. So that's the construct of a MapReduce. But MapReduce system is much more than that. MapReduce system is a system which helps you manage this whole execution model or the programming model, how it can be brought to life. That whole construct is getting enabled through a MapReduce system. So let's get into the details of a MapReduce system. So what does a MapReduce system usually have? Obviously it will have the way to execute a MapReduce job. So that's the first thing which will have. It will have a model to execute a MapReduce job. It will also have a mechanism to say that which data will be pulled out by which node, and which node will process what. So the decision factor and everything is controlled by the MapReduce system. The next thing which the MapReduce system also look at it is you have the data, but between the map and reduce, so there are certain things which needs to happen in the data. So the framework will automatically take care of that. The system will automatically take care of that. So that's the key thing which the framework brings in. Then if one of the machine fails, what happens to the job which is submitted there? Do we need to physically go and recover? No. This framework will itself detect that yeah, there is a failure, and I know what data I have asked it to process. So I'm going to take that same data and ask somebody else to process and give it. So that can be fully automated because now it is stateless. The second construct is each of them are independent processing units, and the central system can control all of this. So that's the construct of a MapReduce system. So Hadoop actually provides you a MapReduce system. It's not just providing you MapReduce functionality, it provides you an entire system. What it does is it helps you to create and submit MapReduce job. It helps you manage the infrastructure to make sure that any node failures and other things are recovered on the MapReduce system. So that is the second thing. The third thing which it does is it helps you decide where the data is local and helps you process the data locally on that machine. So that is the third thing which it tries to do. And it ensures your fault tolerant as well. So that while the execution, if there is some failure, it will auto recover from itself. So this is all the characteristics of a MapReduce system. So let's go back to the presentation and look at it in more detail. So what we see is that the Hadoop system is providing a framework for MapReduce execution. The next point which you need to know is programming model is obviously language independent. It has given you fault tolerance. It does. The whole system will make sure that it is managing the inter-process communication, which means there is no process-to-process communication directly, but the data and other movements and handshake that I have done, I have finished, all that thing will be done by the system itself. So the system manages the inter-process communication. So let's go back. Let's go back to the two things which we left out. One is the complexity of distributed processing. So first let's look at what are the complexity involved in a distributed processing model and how the whole thing works around. So in a distributed programming, so what we are saying is, so I understand that you guys know about Hadoop and what the HDFS does and things like that. So to get there, let's say, so you have a 100 node cluster. Each of the 100 nodes has some data locally getting replicated on the disk, and so we are trying to process one file, one large file. which is distributed at 10 nodes in the cluster. Now, if you don't have a MapReduce system or things like that, first challenge which we'll be looking at is how is this data distributed across this cluster? How is it partitioned? Do I need to manage a partition key separately? So if you look at the database world, that's what we do. We partition the data. When the data becomes large, we store the keys of the partition, and then the whole engine works around with this partition to say that, yeah, this data is this here, this data is there, and accordingly submits the jobs there at each of this location. And once the job is getting executed, the system has to manage whether the job is running properly. Did the job fail at that particular node? So imagine a 100 node process, and if you have to manually go ahead and monitor each of this and say that, yeah, this job has failed here. Okay, now what do I do? I start another one. Where do I start? So the complexity involved in managing that 100 plus processes itself is huge. So that is one complexity you are looking at. The second complexity obviously is the failure case, where something has failed, how things can be abstracted from that. The third thing is, so how do you communicate the status and other things back? So there is a status which is happening, I have finished my job, I am waiting for new jobs to come through. So that is another one. How do you know what capacity each machine has? Some machines might be heavy, some machine might be light, some might have other processes running, some might have a lower memory. So how do you ensure that you do the right thing at the right time? So those are some of the complexities. It is not just an exhaustive list. So once you start programming distributed computing yourself without really going to the Hadoop ecosystem, you would really see the complexity, and you would say that, yeah, it's really a nightmare to do a distributed computing programming all by ourselves. So that's where the popularity of Hadoop, and that's where the whole movement which has started in the last few years, and people saying Hadoop is taking relevance. And if you look at that, the root cause of it is simplicity. What Hadoop has done is it has simplified the distributed computing for the rest of the world and said that, folks, you don't worry about distributed computing itself. I will take care of giving you a framework which helps you manage and distribute your job across your cluster. You can seamlessly bring new nodes up, just start some processes, and that's it. And then you are all set for distributed programming, and you don't need to program it very complex. All you have to do is just program using map and reduce function, two simple functions. You write it, and I will take care of running the whole distributed computing behind the scene for you. So that's what has made Hadoop so popular. That's what has made what we are doing today, because otherwise this whole system would not have evolved, and the big data journey adoption into the market would not have been that relevant. So this is the fundamentals, and you need to remember there are two things which we talked about. One is the MapReduce as a programming model, and that consists of map and reduce function. The second construct is the MapReduce system itself, and don't underestimate that, because that's the power. The distributed system or the MapReduce system which has come through has made it all possible. So that's what I really want to emphasize on these two slides, and I hope the message is clear. There's one more thing. If you want scalability, you basically go to something called as the shared nothing architecture. The shared nothing architecture is where there is nothing shared between two processes processing the distributed processes. So what it really means is, so you have your own CPU, your own memory, your own hard drive, on which you work. Every process works. They don't depend on something like a shared SAN or somewhere where things will be stored separately in a common place. You pick it from the common place. So for a Hadoop system, everything is local. It tries to be as local as possible. So everybody has their own CPU, memory, and disk. Now what HDFS has enabled is to just make that look that as if there is a common place. So that's the beauty of HDFS. So even though it's a shared nothing architecture, from a programming perspective, you will never see that, yeah, there is nothing shared. There is always something shared, which is HDFS. But that sharing is more at a virtual level rather than a physical level. So that's how the shared nothing architecture is working, and it makes it more and more powerful. So going back, the key features of a MapReduce system. Okay. So this is what I covered. I don't intend to spend more time about it, but what I really wanted to cover is, yeah, a MapReduce system automatically takes care of managing a distributed server, which is what we talked about, running the various tasks in parallel, managing all the communication. It's not inter-process communication where process talks to each other. It is about the status, then the function of the job itself. The data transfer between the various parts of the system are also getting used it, and what it looks like is the redundancy and failure as well. So the whole process comes through from there. So let's get into the little more detail. We'll understand what's MapReduce, and then we go from there. So now we understood the concept of a MapReduce. We understood a MapReduce system itself. Now let's keep the system aside for a minute and only focus what is MapReduce. First we will crack what is MapReduce. Once we finish that, then we'll go back to the system and see how to use it. So to start with, MapReduce consists of two phases or steps, we called it, which obviously is map and reduce. So to explain what a map and reduce does, to begin with, first you look at it as a map and reduce are nothing but pure logic or pure functions. It takes some data, it does some processing, it gives some output. Map is doing the same. Similarly, reduce also is doing. The only thing is what reduce takes is might be a little different. It is not just taking an input as simple as that, but it also takes some input, it runs some logic and creates some output. So map is also doing the same thing, reduce is also doing the same thing, but with a slight difference. Okay. So both of them are nothing but functions or logics. That's the first thing which you need to remember. Now let's go to the next part of it. What is the input to a map function? What is an output of a map function? To make life simple for all the people and make it all standardized, we need a framework which will take something which is very standard and make it standard across, so that a lot of the programming language will support it. Lot of the programming challenges which we have can be solved. So the whole construct was that having a key value pair as an input to a map function would really make it more simple. So the whole thing around something like key value pair. What is a key and a value? So any data which you pass into the map function will always have a key and a value. So what happens, let's say you have a text file and you want to pass a text file to the map function. So one option is you will say that let me number each line of the text file as the key. So line number 1, 2, 3 like this as the key. And you can say the content of that line will be the value. You can pass it that way, no problem. But the only catch is you will have to create or generate the one-up number, because by default the text file will not have 1, 2 or 3. The second problem is that if the system has to automatically create that 1, 2 or 3, it will not be able to do it so easily, because the text file now is getting split and going to get processed in a system in 10 different places. So you don't know which part of the file a particular node has got it and where the number starts it. So it will never know what file and where starts it. So the whole thing is key value construct. When you're looking at passing a key and a value to a mapper, it is not something which you derive on the fly. Remember that. It is not something which you derive on the fly. It is the thing which should already exist on the file. If it doesn't really exist on the file, or it cannot be deterministically decided by each of the nodes on the cluster, that key would really not really be a key which you can use, or you can just throw a random number at it. That's the best you could do, because creating a key which is distributed will become a complexity and also a scalability issue, because every node has to know what the other guy has actually assigned a key number, and then accordingly assign the next number and things like that, which essentially means now we are making process dependent on the other guys, which will defeat the whole purpose of scalability. You can still do it, but the scalability will be gone. So the whole idea is that map function always takes a key value as an input. When you say the key can be something which the user can decide, and the value also which the user can decide. So if in a case of a text file, the Hadoop system itself creates the key for you, and the key is nothing but the byte offset of the file itself. So what you have been given is a byte offset of where the record is being read, because when you are reading a record, you obviously know how much is the byte offset from the start of the file. So that's what the value you get as a key, and the value is nothing but the line. But this is for a text input file. But let's say you give it a file which is a pipe delimited file, okay, and you wanted to give a file which is having two columns. The first column, let's say, is the employee number, and the other column, let's say, age, and they are pipe delimited. And you want to write a system where the key is nothing but the first column. You can do that. You can write and say that for the map function, the key will be the employee number, and the value will be, let's say, the employee age or salary or whatever you want to give it. So that's the way the map takes input. So map takes input as key and value. And what does the map produce? Map produce an output which is again key and value. So what happens in between? In between, whatever logic you want to write, you can write. So you say that for the employee, we are getting, let's say, the birth date, and you want to calculate the age. So you can write the age calculation function inside the map function and emit the age outside. So for a simple function which is doing a age calculation in the mapper, it is taking the employee number and the birth date. It is trying to do a age calculation inside the mapper and emitting an age, employee number and age. So I hope the key concept is clear. So the key value is like employee number and the birth date, and the value at the output, the key value at the output will be employee number and age. So the map is doing just the age calculation. So it's a map function. So you should look at it the same way. So if you are looking at processing a text file, the key will be offset of the file and the value will be the content of the file. And usually you can do nothing with that key. So you would really eliminate that whole key and use the value, and you will try to work with the value. So it need not be that the map input, even though you are taking key and value, you need to use the key and value for your advantage. You don't know. Sometimes we only use the value and create the keys from the value itself. So, but the only thing is the programming model has been made general. So that's what the map function is all about. To summarize, and what we need to clearly remember is, map is a function. It's a logic. You can do whatever you want inside that logic. The only constraint you have is it will take key value as the input and give key value as the output. And the input key and value doesn't need to be the output key and value. You can change it whatever way you want. So that's the map function. So let's go to the reduce function. The reduce function will take key and the list of values. So what it means is, the reduce function usually takes a key and a values which are associated with that key. So for example, in the map function you had an employee number and you had a birth date. But if there, let's say there are 2 records for the employee, for a particular employee there are 2 records, then the reducer would have take employee number and both the values for that particular employee in the same record. So that's the least of values. So what you are saying is you are doing a group by and passing it to the reducer. So in a text, in an RDBMS world, what you would have done by group by is precisely what is happening at the reduce side. The reduce side is taking key and a list of values for that particular key as input and giving an output which is again a key and a value. Again the key and value you can decide your way. The reduce function is also the same. You can write whatever logic you want. The only thing is you now have access to a key and all the values for the associated with that particular key. And you should be guaranteed that once you process that particular key record, there will be no duplications you will receive. Like all the duplications would have been eliminated and it will be grouped by key and you would have got it. So reduce function always makes that assumption. Reduce function always makes the assumption that the key is going to be unique always, and all for that key whatever values has to come in, it always will be in the list of values. But map function doesn't assume that, make that assumption. In a map function you can have employee number repeating in multiple rows and given to the map function. But in the reduce function, it will always assume that the key is unique and there will be no duplicate of the key which will come. So that is the fundamental thing which the reduce function will do. So I have just explained 2 concepts here and I hope that's what I want to summarize here as well. The first thing, map is just a function. It takes a key and a value. It gives out a key and a value. Inside the logic you can do whatever you want, no problem. There is no guarantee that the keys will be always unique. It can be the same keys also coming again and again. So that is the map function. Reduce function takes a key and a list of values. It will always ensure that the key is unique and guaranteed so that you don't have to worry about duplicates which will get it. The logic you can write again anything inside the reduce function. The only catch is you need to make sure that you emit a key and a value as an output. So this is the key things which you need to remember for a MapReduce, map and reduce function. So why is MapReduce so popular? MapReduce is so popular because it is so simple. Because every map function operates on the input which it is received. Every map function emits the key value pair. And there is something which will happen between a map function and a reduce function, and that is called the shuffle, sorting and grouping of the output of the map function. And once that is done, it goes to the reduce function. The reduce function again does the logic and emits the output per group. That's the only difference. Okay, so here is a simple example and we will take this example to explain MapReduce further. So we have a large collection of a text file in a folder. So assume that you have 1000 documents and each document has an average of 1 million words. 1 million different types of words. It's an English document, let's assume for now. So this is our problem statement. And what we need to do is we need to count every word and for every word how many times this has occurred in all the documents. This is our problem statement. So you can think through maybe for a second to look at how you would write it in a Java program. First of all, now since it's a large set of corpus of documents, each having lot of words, you will not be able to run this on a single machine, which essentially means you need a Java program which will process data from multiple machines, which means either you can write Java programs which which are multiple Java programs talking to each other and doing all this count at each of the stage and trying to pass that values to each other, calculating the aggregates, coming to the values and stuff like that. Just imagine how you would write this program without having a programming construct like MapReduce. The thing is, if you try to attempt this, I'm sure you will spend maybe months and still not crack this problem with simple Java techniques. It will not work because you will try it. Once you try to crack the logic, then the node failures will start happening. Then your disk failures will start happening. Then you will have inter-process communication issues. Then you will have network failure issues. And by the time you handle everything, I think it will be years before we can write a Java program which will really solve this problem. And in MapReduce, you can solve it with 10 lines. So that's the difference of MapReduce on Hadoop. How can we write such a large program which will read all these files, aggregate it each level? For each word, you need to aggregate. So that aggregation itself is a complex affair, in the sense that to make sure that for every word you need to increment, you need to have a database where you will say every word, you keep on incrementing the count for every word. And by the time you increment, since you are processing on a large scale, there is contention, locking issues and things like that. And you get into more trouble. So those are the other challenges which you are trying to solve a problem in Java without using the MapReduce programming model. But with MapReduce programming model, this will become a very simple problem to solve. So what you need to remember is, you would have written a lot of programs in Java earlier, lot of things where we have written a lot of complex logic. If you start thinking the MapReduce way, you would be able to simplify that program even in your Java world without even leveraging Hadoop. So that's the one key learning which you would still want to take it back and see how you could actually simplify a lot of logics by just applying the MapReduce techniques even there. The only constraint is that you need to make it state independent. So that's the only catch you will get to. So anyway, let's go back. Let's take it to the next level. Now we will look at a simple MapReduce program, how to solve this. So we talked about map function. We said map function will operate on a key and a value, okay, and transform the data based on the transformation logic which we have provided in the map function. So the map function always emits a key value pair, and so this is the mathematical representation of what we just talked about, a map function. A map function takes a key 1 and value 1, so that's a key value pair, and it will give out key 2 and value 2 as the output. Map function transforms is similar to a row level function in standard SQL, which means it is not doing any group by. For every record here, you could actually emit one record output, but you need not be like always you need to emit anything, but you could do that, which essentially means we are just transposing the key and value to a different key and value. Okay. So for this particular example of a word count, what we would do as a map function is, we will say that we will take every line, we will split every line into words, and we will emit word, and let's say for a, now we just say that every word we found, we say 1 as the value. So the key will be word and the value will be 1. So what is the map input function? The map input function will be, let's say the key, in this case this will be the file offset, value will be nothing but the line. So in this particular map function, we are not going to use the key 1 at all. In the function, we are just going to take the value, we are tokenizing the whole thing, we are creating a new key called word, and we are creating a value called 1 and emitting it. So this is a clear example where we would not be using this key 1 at all. So So you don't need to really use this key1 and value in your map function. You can do whatever you want separately also. All it requires is this will be the input signature, this will be the output signature. So for each file, the map function will be read each line from the input file, tokenize and get each word, and for each word emit word and the 1. So this will be what the logic you will write in the map function. You will not write anything beyond this. You will write only these 3 lines. The word 1 will be forming a list that is going to get separated. So this is the output. Word comma 1. Word comma 1 is the output. So in this case the word will be the actual word in the text document. So let's say the document has read each line from an input file. That's what the thing will be. It will emit read 1, each one, line 1, from 1, the 1, input 1, file 1. Like that it will emit. So it will emit for every word, it will emit 1. So remember that there will be duplicates. So let's say there are 10 lines here and each line has read each line from the input file. This word read will be emitted that many times. It will not really aggregate or do anything. It will keep on emitting word and 1 from the whole list. So this is what will happen in the map function. So before we go further, you are assuming that you have got each line from the input file. But how do you know the large file which we have given is now broken into multiple files, and even if the file is too big, how the file is getting split and passed it to the map function? All that is done by the framework. All that is done by the framework. You don't need to do all that thing. You just need to tell the function, the system, that this is the location of my file, okay? This is the location of my file, and this is the map function, and I am going to use a text input format. So the moment you say it is a text input format, the system already understands. The system already understands that it's a text file. I am going to make the key as a byte offset. The value I am going to give it as a line. I will read and split the file based on the data locality on the node. I will give each mapper a line out of that split. That's all taken care by the framework. So that is what it makes it so simple. So when we said Hadoop makes developers' life easy, this is what it has done. It has given a programming framework, which is the MapReduce system, which makes it life so simple for you and us that you only focus on the business logic and you don't worry about all the challenges of distributed computing. The framework takes care for you, everything. All you are doing is you are only focusing on the business logic. And in this case, how do you break this problem of counting words into map and reduce functions? If you want to take a break on that, I can go there and we can see how the whole system will work. So let's look at that question precisely, because that makes it more clear what really happens in the system. So the whole system of MapReduce system will take care of doing everything for you. That's the blanket statement I have made. Now the question is, how does that works internally? So for that you need to understand there is the HDFS file system organization itself. Let's say you have a 1 GB file which you have loaded into HDFS. So now you might have a 100 GB file, you might have a 1 GB file, you might have a 100 MB file. So in this particular example, let's say we have all the three. Okay, we have a 10 GB, we have 1 GB, and we have 100 MB file into the system. So when you look at how HDFS will store it, HDFS has the block size. So which essentially means that let's say I give a 1 GB file to name node for storing. So basically if you look at the whole programming model, what we do is I take my 1 GB file from my local disk and write a client program or invoke the Hadoop client and tell to the Hadoop client that, boss, I have this 1 GB file which I want to store in HDFS. The Hadoop client will then contact the name node and ask, name node, give me the locations where I can store this file. Name node will have the list of all data nodes which is associated in the system, and it will know precisely which guy has space, which guy doesn't have space, what are the blocks which you can do. So name node will do all that magic calculation and send a list of data nodes to which the file has to be sent and in which order it has to be sent, in the sense that where the file has to be broken and sent. So the Hadoop client already knows what is the block size. So it will take this 1 GB file, split into different blocks. Okay, and name node would have told that send this block number 1 to 20 to this data node. So the Hadoop client would ship that data to that particular data node. The data node process, okay, will take care from there and push it into the data node at locally there, and also take care of making sure that the replication also is initiated. So basically it will do a int and off and things like that to make sure that the rest of the people also gets it and they will be able to replicate across the cluster. So that's the storing part of it. So now the data is stored, the 1 GB or the 10 GB, everything follows the same thing. It is just broken down into blocks, handed over to the data node. The data node takes care of storing it. Okay. Now the file is distributed in the cluster. It is distributed in the cluster in at least 10 machines or 20 machines depending upon the block size and things like that. So now let's say we are trying to run a MapReduce program on this file. So what we have done is we have given a full directory to this MapReduce function. So the MapReduce function is basically submitted to the job tracker. Okay. So job tracker is being assigned the task to say that, boss, now run this MapReduce function on this particular folder in Hadoop. What it would do, it would think like how this file has now to be, where does this file exist. So because it will contact name node, it will understand and find out where is the locality of this data existence. So which also it will also check the system to figure out where all the tasks, the available slots for running this program exist, because every task tracker inside each of the Hadoop will define what is the slots available for execution. So based on the slots available and the data locality, the task tracker will decide where it should execute. Okay. So now once it has decided that, okay, I'm going to execute here, and then there are a lot of policies in the task tracker to say how it should execute and where it should execute and stuff like that. So let's assume it has decided, yeah, there are 5 different task trackers on which it needs to execute. So what it will tell the thing to the task tracker data node is that, data node, please process this part of the file. So it will give you then the block number, because it knows precisely which task tracker has which data, which basically the locality of the data based on the data node's publications. So it will tell that you need to process this particular splits of the file. So the entire file is now split into blocks and it is assigned to the task tracker. So the task tracker now intelligently knows that I am supposed to work only on this block of data. So what it will do, it will take the file from the particular block and pass that function to the whole MapReduce function, and it will give the offset of that file from where it has picked up. So what is the file offset? It will know, and that file offset is what it will pass it to the map function as the key. So this is how the system will work. There is a little more complexity. I've just still tried to abstract as much as possible to make it simple, but you could see the value of the MapReduce system or Hadoop itself. You want to do such a large scale computing, you would have to write the whole thing yourself. Now what the whole thing has happened is the framework is doing everything for you. All you are doing is You are writing a small map function and telling it to the framework that was just execute. The whole thing happens behind the scene. See, the offset is not stored. It's taken from the file. As you read the file, you will know the offset, correct?
Job tracker and task tracker, right? Task tracker will initiate the mapper, and mapper will initiate a number of instances on each each block based on the storage of the system, the cluster or whatever the nodes. Okay, like at the same time, think about in this case, in the given scenario, what you gave, 1 GB, 100 MB and 10 GB, there might be tons of mappers will be running parallelly.
Correct.
Okay, if that is the case, how do you get the offset for each? Like there are things that 10 mappers are running parallelly. Okay, when the file starts from one place, so even the 10th block will be running at the same time.
So when you store a file in the Hadoop system, okay, you store it in the form of blocks. Okay. Now, a particular block is getting picked up by a mapper. Okay. Mapper is not picking up multiple blocks at the same time. Every mapper is picking a single block at a time. Okay. Now, every block has the metadata of the offset, because that is the only way it can construct the whole file back. Okay. So when the file is stored, it already has that offset with it at the start of the block.
Okay. Then,
so that is what it takes from there.
Then you mean to say that like the offset should be stored in somewhere in the metadata, right?
Yeah, it is there in the because the data node knows it, because otherwise you will not be able to join the file back.
Exactly, yes.
Okay, so it will not be able to store the file back because that part information is there in the metadata itself. It is just that the file, see why I said it is calculated is because, so when the first record starts up, okay, it knows what is the offset because that is by default stored. The next line comes up, it is incrementing the offset and reading it.
Right.
Got it? So because there is a particular block of file which it is reading, it knows the starting position. First line goes through, it knows how many bytes I have read. The next is offset, next offset, next offset, next offset. Okay. And even if you are running 10 jobs, everybody is running on one particular block. Everybody knows their stuff. Okay. So, and it is sequential after that. So, it is parallel across the blocks, sequential within the block. Remember that. So, given that, you will always make sure that you are having a offset. Now, coming back to this offset business, okay, this offset business is useless. I have not seen a program where anybody has really used this offset. Okay. Because offset is a file physical offset. All you can tell is that whether if you print that offset, you can say it looks good because the file is reading sequence. But other than that, you hardly have any use of that offset. Okay. So usually what we do is when we are reading text file, we make that the value is what we read. There are other ways to do it. Okay. So where we change the input format and create our own input formats and decide what we need to pass as keys to the things. So that I will cover as we go to the end of it to see how you can do an advanced programming in MapReduce, where what are the things which you can change within the framework itself by overriding certain functions. We are going to write a very small program. That's what the whole message is. It is not a complex affair. The whole challenge is about how do you dissect your problem statement to a MapReduce problem. That's the biggest challenge. It is not about how to write a map function. The moment you crack it saying that this is my problem statement and I am able to visualize this function, this logic as a map and reduce function, job is done. Writing that map and reduce function is the most trivial part of the whole equation. Okay. Remember, the whole reason is that how do you think the problem and convert that problem to a MapReduce is the bigger problem. And that is the skill which you need to acquire. So when you would be seeing, I am spending more of the time on the theory because the reason is writing a map function is a simple task. It's just a Java program. It is not the complexity. But how to think in MapReduce is the real problem. And you need to really have that hang of it as we go through the course. So I would recommend everybody to focus on that one aspect, to say, how can I think in MapReduce? How can I take a problem statement and think in MapReduce? That's what we need to look at. Once we crack that problem, the second problem is very simple. Writing a map and function is, as I will show you in the Java code, it's like 10 lines. If you are writing Python, it will be 3 lines. If you are writing in any other program, it will be similar. So the coding is simple. It's all about concept. To the reduce function. So before we move to the map function, move out of the map function, I just want to emphasize one more very important thing. You should remember map function as a function which operates on every input record. Remember that way. Even though it is operating on a key and a value, forget the key and value for now. Remember only one thing, that a map is a function which operates on every single record of input. Okay, so it is taking every single record of the input and transforming that record into whatever you want. And the output also will be either multiple for every one line, you can eliminate some lines, but you can never aggregate across lines. You will not be able to aggregate across line. Remember that in a map function. Because you will get key and value at a time. You will not get two key and value at the same time. The only thing which you can do is, if you can preserve a variable inside your map function, and since it is going to be a Java process, that variable will be in memory till that particular mapper executes. So that's the only guarantee you can get it. So if you are trying to do some stateful processing, that's the only advantage you can take, saying that every mapper can be guaranteed to execute without the JVM coming down. So again, what I wanted to emphasize is map function always operates at every record. That's very important. So that's the key thing which we need to remember. So let's go to the reduce function now. Reduce function takes a list of values for every key and transforms the data based on the logic. And I said that it's aggregation logic because now you are getting for every key what are the list of values. So one thing you can do is you can take all the list of values which for that particular key and do an aggregate function on the list of value within the reduce function itself. Because you are transforming from the list of values to a single value. You see that. So that is how the aggregation logics can be written here. Otherwise, you could actually do anything basically with this list of values. The only thing is you should emit not as a list, you should emit as a single value. So what usually also happens is that you don't want to do an aggregation function. You want to do a split function. Yeah, you can do that. What you will do in the reduce function, you will iterate over this list of values, and for every iteration you will emit, which is possible. The reduce function is not enforcing that for every K2 you need to emit only one record. No, you can emit all the records one by one. So it's not a problem. So, but in a typical case, we use the aggregation logic inside it. So what a reduce function does is, it acts like more like a aggregator for you, because it will always get a key and a list of values with it. And what it will do is it will just take the key and list of values and perform something. So it's like an aggregate function in a SQL statement. So for this particular example of word count, so let's go to that particular case and see how the program will be written. So what we saw in the mapper output was that map was giving the word, basically whatever the name of the word was, and it was giving 1. Now before that word and 1 comes to the reducer, the framework will do so many things. The framework will first sort on based on the key. Okay. So first it will sort based on the key locally. It will sort and keep the files locally there. It will also try to group and give for every key what are the list of values it will give to the reduce function. So reduce functions are run on a different nodes in the cluster. So the data will actually move. The data will actually move from all the map functions to a particular node or a bunch of nodes which are going to run the reduce function. The reduce function will always get the key, and in this case it will be the word, and it will get a list of values. List of values. Since we are emitting 1, 1, 1, 1, if the word is occurring like say 20 times, each we will get word and 20 of these ones. Okay. So in the reduce function what we are going to do, we are just going to add all the list of values, and for that key we are just going to submit it. So the key thing is, again, when you see the reduce function, ideally we are doing nothing here. We are taking a word, list of value, just adding it and out. That's the only code we are writing. But the whole thing of shuffling, sorting, grouping, everything is done by the framework. So that's the beauty of the framework. The framework will take care. See, the whole magic is done by the framework. Okay. Yes, the framework is trying to aggregate that and give it to you all the distinct part of it. And the framework does a lot of work. Okay. Okay. Because there's a lot of work which is going behind the scene, because you have to imagine, and we'll cover that in detail as we go through how the whole system works internally to figure out and get you the whole thing, because the reduce output, not the reduce, the map output are located in each node of the cluster where the map is run. The reducers are going to run on some of those nodes or a different node. There is no guarantee that where it will run, because that's what is decided by the...
That number of mappers depends on the number of nodes, right?
No, the number of mappers is not decided by the number of nodes. There are multiple things which will happen there. In fact, you can control, okay, you can control how many mappers to execute, okay, by a parameter, or the system will pick up based on how many splits are there, how many slots are available, and what is the best thing which it thinks it runs. But you can also control and say, it don't run, I want precisely 5 mappers to run, okay, or you can say precisely run 1 reducer. So you can also control, but the framework also can decide based on its intelligence. So the number of mappers is usually decided based on 2 criteria. The number of slots, free slots available on the cluster. Because once you set up the cluster, you would have seen the cluster sign. When you are setting up the cluster, you give a configuration in the properties file which says how many map slot and how many reduce slots. Okay. So every nodes will have map slots and reduce slots. And the task tracker also will be communicating to job tracker how many of those map slots and reduce slots are already occupied by previous jobs. So job tracker precisely knows what is its capacity to run. Okay. And based on that, it will decide how many mappers and reducers to run. Okay. So that is one way. Otherwise, you can actually decide by setting the parameter yourself while giving the job as well. But it doesn't mean that even if you say I want 100 mappers, parallelly 100 mappers will run. No, parallelly 100 mappers will not run if there are no slots. Because the task tracker knows that I cannot run 100 mappers. So task tracker is going to run how many it is available. But it will ensure that the input is split into that 100 mapper slots, and thus there will be 100 mappers which will eventually run. That's the catch.
I think that even the data is spread across like 10 different data nodes. Then still we can limit the mappers to 5.
Yes, you can limit it to 5. The only thing is, if you limit it, there will be lot of data transfer which will happen, and your jobs will be inefficient. Okay, it doesn't mean let's take an example in this case. So you have a data node which has the data, okay? But that data node has no task MapReduce slots available. What it will do? It will run on somebody else, okay? And it will pick it from there. So that is what it will try to do, okay? But the catch is it will be very inefficient, because if you are running multiple blocks, okay, so there is a minimum set also which is required based on the block size, because every block is going to get split and it is going to run. So now if you increase that, the efficiency is going to go down drastically.
So if there are 10 blocks distributed across 10 nodes, and if I want to run only 5 map jobs, so probably every mapper will work on 2 blocks, you mean to say?
Yeah, every mapper, it will have to still get that second block and it will run. So it will still schedule the mappers to get it executed. So it can do the process. There are two patches there right now. Okay.
Now each mapper will be having the different instances, right? It can have any number of mapper instances, right? It doesn't mean that like one mapper will run only on one data node. Okay, think that one data node having like 100 blocks. Then like one mapper can initiate any number of instances of the mappers, right? Parallelly it can start.
See, once a mapper starts off, it has the input splits available to it. It will process those mappers, the input splits through that mapper. It is the reservation of the slot. It is nothing beyond that. Okay. So now if you have 10 blocks to be, 10 splits to be processed in that particular node, it will process it. It will only sequentialize it. It will fork off a GDM process, give the data splits one after the other. So the whole idea is that you make sure that you make it efficient. Usually when we give, we don't really specify the number of mappers to run. We only specify the number of reducers. Okay. Number of the programs which I had run, I have actually done a mapper specification. We don't really say. We will let the system decide, because that's a function of the number of block size and the input which it needs to process. And based on the capacity available, let the system decide. So we don't usually specify the map slots to use. Okay. It is only the reduce slots which we say to use it because of two reasons. One is we want sometimes the reduce function to operate on a single node, because I want all the data from the mapper to go to a single reducer, and that's the only place where we do that. So what I was saying is precisely on the reduce function, we actually supply the number of reducers, and that too because we want to control whether all the data should go to a single reducer or multiple reducer. That's the reason why we would specify a reducer number of slots. Otherwise, usually we let the system dictate and finish it, because if the slots are available, it's better to process it faster and finish it off. Why do we need to control it? Because anyway, it is independent of that control, that it is still going to do the same thing. So if there is already capacity and it has the authority to execute that, well, why not let it execute? So that's the whole idea, that we don't really control the MapReduce and reduce slots. Instead, there is something called as capacity scheduler and the fair scheduler. What we do is we try to give a slots to each user and say that for this particular group of users, this is the capability which you have, and that's pretty much what we try to do. We try to give them a slot based on the scheduler capability. So if you are looking at advanced concepts, there is something called as fair scheduler, capacity scheduler, where a group of users is given slots, and based on that slots is where the whole thing will get executed. So this is the code which we would have written for our map function. Okay. So you will write inside a map class which will extend a mapper function, and you will write only this code. So we will come back to the int writable and all at the end of it, because they are all boxed data types which are specifically tuned for Hadoop. So Hadoop doesn't use any of the standard data types by default for the framework, because it needs multiple features on that data type itself. So what it has done is it has tried to write all the data types by themselves. The string, the int, everything they have written it themselves, so that it makes it more easier for us to use the framework. So in this particular case, what we have done is we have instantiated a static variable 1 so that we can pass it here. When you are emitting, you are just passing it 1. Okay. So that's the int writable which you have written, because the signature of this in the world of Java is pretty well defined. So let's say the map function, it's taking a long writable key as the key value. So this is a long writable. This is where the offset is going to come. Text value, because we are using a text input format, the value is going to come as text, and this is the context which you can use it for reporting, and everything else is done through the job context. Okay. Now I have thrown some couple of exceptions here because of the functions which I am using, the IO exception and the interrupted exception. Interrupted exception should be definitely there because we are going to interrupt it. So first line is you take this value and convert to string, because this is text. You have converted to a string. Then once you got that line, now you have used a tokenizer. Now what you have done is, once you have tokenized this, you have got each word into this token. So you are iterating through that token one by one, and you are setting the word as that particular token, and you are then immediately emitting that word and a int writable which you have set. So this is the map code, nothing else. This is just a Java implementation of this map code. The map code pseudocode which we had written some time back. This is the pseudocode. This is the pseudocode. Read each line from input file, tokenize, emit one word. This was the thing, and this is the Java code. So each line is coming here. The framework will give you that. This value, if you print, you will get the byte offset of the file. Okay, and all we are doing is we are taking this value. We have not even taken the key at all. We have ignored the key totally. We have created the key from this value by tokenizing and generating the word. And so now the key is become this, and the value of 1. 1 is a hard-coded constant 1.
So for every line this function is getting called? Or?
Yeah, for every line in the text this function will get called.
And it calls very parallelly, right? With the
Yeah, it is running parallelly across all nodes and mappers and stuff like that, and it is getting this for each split, for each block, for each line. This function is getting called. So this is the reduce function. Now what happened in the reduce is that we have got the key and we have got the value which is coming in. So what we have done is we have set sum equal to 0. We have initialized the sum for each list of iterable values. Okay, we are just adding that value and then emitting the sum. The only thing which we have done is we have boxed the sum, because this was int, we have boxed it to int writable. So reduce function is getting a key and a list of values, and for each of them there is a sum which we have initialized. Now this sum is getting initialized to 0 for every key, remember that, because there will be no duplicates. So every time for every key you are initializing sum. Now if you remove this sum equal to 0 and you would have instantiated at the mapper level, you can aggregate, at least sum up across the values of keys, but only for that particular reducer. Remember, it is only for that reducer. Now if you would have set the reducer count to 1, okay, if you set the reducer count to 1, move this in sum equal to 0 out of this reduce function, what you would get here is basically a total sum. And in this case, you would not emit this key, you would emit something else at the end of it. So the last value obviously will have the total sum. You will get an incremental sum for every key as it goes through, and the last key would have the final sum, if that is the case. But in this case, we are not going there. We are just trying to create the word frequency, and for each word, the sum is getting initialized to 0, and then we are getting the value.
Yeah. This piece will run only once all the maps are run. Maps running is over. Then the start, shuffle, everything is over. Then only this will come into picture, right?
Yes. So now let's look at the sequence of operation. The sequence of operation will be, first it will split all the files. It will assign all the map tasks. Okay. It will send all the map tasks to be executed. Now once each mapper will finish their own task, okay, and then they will create a local file in their own instance node. Okay. Now at the same time, the job tracker would also have instructed that this is the kind of reducers which we are going to run. So you need to bifurcate by keys and keep it. So the job tracker itself, the task tracker itself would have actually sorted the file, okay, and based on the keys, and created buckets of those files, created and kept it ready based on the number of reducers key hashing which will be done. Okay. Now once all the mappers are executed, the reducers will start showing up. It need not be that the reducer has to be started after all the mappers are finished. The reducer operation will start before that, but reduce operation will not be called, because the reducer itself has to do so many things. It has to go to each node where the file will be, and it has to pick the file for that particular reducer, because there are 10 reducers running. Then each reducer will be given a key range on which it needs to operate. So that key range, it will go and fetch from all the mappers the files associated to that key range. It will ship that file from that node to this node. Okay. So like that, it will start bringing files from all the nodes. Then it will do the shuffle and sorting. Okay. So the data transfer between the node to the reducer will happen upfront. It will not wait for the reducer mappers to finish. The data transfer will happen as soon as possible. But the reducers will not start executing. Once all the mappers finishes, it will start sorting up the results. Once the results are sorted, and then it will group it and then pass it to the reducer. Then the reduce function will start getting called. So this is the sequence. So when you run the job in the console and you start saying that map is 80% done, reducer is 10% done, that will be the status you will see. Okay. Why reducer is 10% done when mapper is only 80% done? Is because there is file transfer which is already happening from those 80% completed mappers to the reducer. So the status is reflecting that file transfer. But once all mappers are finished, 100% reducer will start moving. Okay?
Yeah, you said something about the file transfer. Can you little elaborate on that?
Yeah, so the file transfer is basically, see, the thing is, let's say mappers have done their task of running the map. Okay, they have created the word and the count, correct? So now word and count is emitted and it is stored in the local cache of the mapper task node, correct? Now reducer will be running on some other machine. Now the reducer has to get that file from each of the mappers. So there is a file transfer which will happen for the result, intermediate result the mapper has given. So that a file will now get shipped to each of the reducers based on the keys, and the reducer will basically pull that file. So there is a inter-node process communication which is happening, but the framework is doing that for you. the logic is not doing any inter-process communication. It is actually the system which is pulling the file from all the nodes to bring it to the reducer.
Okay. What is the role of this context here?
See, the context is the handle which you have to write. See, the context is basically saying that if otherwise there is no place where you can write. You are not creating a physical file, correct? It is a handle to the system file context where it will run and it will write the output. So this context will internally access the mapper, the output file location and put the file into that location. So what does this context really helps you with is, it is your gateway to the framework. Okay. So what you are doing is you are just writing it to this context and insulating yourself from worrying about the file handling capabilities and all other capabilities which the framework is doing. All the framework is saying is, you please write it to my context, I will take care from here on. So you are just passing, you are handing over your data to the context to the framework and saying please handle. Okay, so the context is for that. The context has like lot of other things associated with it, but it is pretty much the file context on which the operation will happen. No, this context.write is available at both the places, correct? So you see the mapper. Reducer case kicks in only for transferring the file, and that too not for the incomplete mappers.
Okay.
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 Reduce file is only for the completed mapper, because otherwise it will be total mess, because there is something called as combiner which we are going to discuss. Okay. So what happens is, now you would have seen that, let's say in a file now the word read is appearing 10 times. So there will be 10 read 1 comma 1 read comma 1 read comma 1 10 times in a particular mapper output itself. Similarly, read can occur in another 10 nodes, correct? But why should we ship that file down to the reducer? Instead, we can ship the value of read comma 10 from the mapper, correct? We can do a local aggregation there itself. So that is what the function of a combiner comes into play. We will cover that combiner separately, but that is what the combiner does. So once the mapper is done, the combiner will start operating there. It will, if you have specified a combiner, it will combine the result, and then that output will be stored. That will be further shipped. Okay.
So the context.write actually creates a temporary file for every mapper, right?
Yeah, the context.write is giving the data control to the framework handler. The framework handler will then instantiate the file and then write. Okay.
Okay. So the method signatures, is it constant or does it change?
No, the method signature is here, clear only. This is the signature. There is no other thing.
So
and if you want, we will pull up the API doc next time. I will just try to get you the API docs properly, so that you can see the API itself in context.write.
Okay, the reduce and map method signature, so it's just a constant one, or?
No, see, the reduce and map is only having key and value as the constant thing. The text are iteratable, this iterable and all can be changed. Okay?
I understood that, but it takes key and iteratable values and then
key value and context, that is fixed.
Yeah, okay.
Okay, so the signature, the parameter count is fixed.
Okay.
The only thing which will change is the data type, and the data type itself will be different. Okay, so now there are two questions for all of you to think through. Okay, the first question is, where do you think the final output of the reducer go? Will it go in the local system or will it go in the HDFS? So the question is,
I think the value should be given to the node which invoke this mapper and reducer.
No, it will not go to the node or something like that, because HDFS is a distributed file system where everybody have access. So the file, the reduced output would really go into a particular directory which you have specified when you started the job, and it will go into that directory.
So, but how would I know which node has the output?
Which node
has the output?
It doesn't matter. You don't need to know it, because it is not node dependent at all. And you will never know it also, which node actually created that one, unless you go to the job tracker, and by the time job finishes, that output will not be there also. It would have got very different.
Okay, I wanted to do a batch processing where I just pass a large file and I wanted to create a list of, I wanted to create a temporary file which is actually an output file. I wanted to analyze it offline. So how would I do
Correct.
that?
So what you would do is you will run a job and you will say that the location still will be HDFS location.
Okay.
Okay. The output will get put into HDFS and then you will have to pull it from HDFS.
Okay. So
you cannot get a local output. That is what I was asking.
Yeah, I understood. So the output file is written back into HDFS, and
yes,
you need to use an HDFS client to pass the output and get the output, right?
Yes. Okay. Yes, and there is one more interesting thing there, okay, in the output part of it. So when you start, there is a driver program also which is required along with these two programs to run it. So you have a mapper and a reducer, and you have something called as the driver code, which is the settings and everything given to the framework. So basically you write three things. You write mapper, you write reducer, and you write the driver. Okay. When you write these three things is where you submit this whole thing into HDFS system. So basically to the job tracker and say execute this for me. Okay. So the driver program is basically telling the job tracker that what it has to execute and when. So it will say this is the class which needs to be executed. This is the number of mappers or the reducer. Basically, if there is a number of reducers which you give, this is the input location, this is the output location. All that is specified in the driver program. So the driver program also gives the class name for the mapper and reducer. So the class, because you don't hardwire it, you softwire it using the driver program. So you can use the same reducer for 10 different MapReduce jobs also, because you can just specify the whole thing. Okay. So now there are two interesting. Okay, go ahead.
One more question. How does if you write to some file, right? So that file is getting written into HDFS. How would the client know the file name? So you pass it as part of the driver program, or?
Yeah, that is where I was coming to. Interesting. There is no file name which we specify in the driver program. We only give the location of the folder because there will be multiple reducers running. Each reducer will create an output called part-00010002 like this. So if you go to that directory, okay, you will see 20 or 30 files depending upon how many reducers actually ran. For every reducer there will be one file. Okay.
How would I know the output file pertaining to my reducer?
No, there is no, see, it is for your job. All the files is for your job only. Okay. For your job, if there are 10 reducers, then on that output folder there will be 10 files. All files are your files only. Only thing is they are split and kept it because they don't want to have contention across reducers. Every reducers will write its own file and keep it there. Okay. Then there is an HDFS utility called merge, which you want to use, you can merge it. We usually don't merge it because the next MapReduce also can take a folder only. You don't really need a file. So if you really need a file, specific file, you can use the merge utility, merge the file and get the file to local also. Okay. You would have done the HDFS commands for that. So there is something called as merge files and get to local. So now the question is, reducer is going to put the output into HDFS. Okay. And each reducer is putting the file to HDFS. What happens to the mapper? Is each mapper putting the file into HDFS or not? The answer is no. Each mapper is only creating temporary local output files. Now, if there are no reducers assigned to the job or the reducer count is 0, then the output of the mapper is shipped to HDFS in the output directory. Okay. Otherwise, the reduce functions only writes directly to HDFS. Map writes to local. Transfer, the reducer picks up from their local and does the whole thing. Clear? Why reducer mapper writes to the local is because writing to HDFS is a time consuming process. Second, HDFS has a default replication factor. So any file you write to HDFS, it will immediately start replicating. So in this case, the mapper output is not something which we want to replicate. So you will keep it local. And also you will avoid the network latency of transferring the file to HDFS. So because reducer will pick it from there. So the mapper outputs are local, reducer outputs are in HDFS. That is the two things which you need to remember. Second thing is, for every reducer there is a file which is getting created. And the file is always created in HDFS. If you want it to get it to local, use the HDFS command, bring it to local.
Yeah, you said that the mapper output is local, right? Local means where does it store in the local?
Local directory. So if you are configuring Hadoop configuration, okay, if you go to that, if you have set up the cluster yourself, you know that there is a configuration in the Hadoop configuration file where you are saying MapReduce output path and stuff like that, local cache directory for the MapReduce. There are directories which you give.
Okay.
That is the place where the file will be. Similarly, log files will be local. The local log files are overwritten. It is not carried forward to the job tracker. So this is one typical problem we always face. Each job runs at each of the nodes. The log files are also local. That log files can be viewed from the job tracker console, but still the log files are local. So if the node is down, the file is also gone. So that's the other things which you need to remember on a practical things. So there was one more question on, can I get a one more example for MapReduce function? Okay, so let's do the same example in a different model. Okay, so I have these three examples which are there. So let's say you got a text file and you want to convert every word into a uppercase. If you want to just convert every word to uppercase, you don't need a reducer. If you want the whole line as is back, you can just write a mapper where in the mapper logic what you would do is you will just convert all the line to upper and emit key and value again. Same key and value. So you will get a file which has the files which are converted to upper. Now if you want to filter a particular set of records and still do a word count, you can do that logic inside the mapper. You can put a if statement inside the map logic and say if this condition satisfy, ignore the record. Don't emit it basically. So that is how you could do filtering. You can do both filtering inside mapper and reducers both. Okay. The last part is, which one more example is there. Let's say you want to get a sum of squares. A sum of squares will be like 1 square plus 2 square plus 3 square plus 4 square. So if you want to do something like that, how would you do that? To do that, what you would do is, let's say you give an input file which has 1, 2, 3, 4, 5 like this and number as an input file to the MapReduce system. The mapper will, what it will do, it will say just 1 square it will emit, 2 square it will emit, 3 square it will emit. The reducer, you can run one reducer because you want to aggregate all of them together. So you will say I will run only one reducer. So which means all the output will come to the same reducer. There you are just going to add everything. If you just add it, the output will be sum of squares. So the key thing is to think in the MapReduce form. So what you are doing in the MapReduce form thinking is, you have to think it in two forms, saying that any problem statement I will break it into two parts. one part, what is the operation I want to do at record level. Move that to the mapper. See what operations after that I need to do, which is aggregate operations. Move it to reducers. Okay. Then you will decide how I would do that in the key value construct. So I will decide what is the key and value. For every problem statement, if there is no input key which you are getting, forget it, no problem. Don't worry about it. Take a text input format. It will give the byte offset as the key by default. Ignore that key. Take the value, and on that value you can split and do whatever you want. Create the keys there and put all your business logic inside that mapper function. Make sure that whatever logic you put in the mapper function is only row dependent, that particular row dependent. You should not depend on a previous row, or you should not depend on something else and maintain state. You don't make it that every operation is a row level operation, and that row level operation you will put it in the mapper logic, and then you will get the keys. Now you want to group by certain things. You know that, yeah, that's the key which I need to emit, because then only the framework will automatically group for me. Otherwise it will become a mess, because you need to know what is your group by key, and that should be the key which you emit from the mapper. And the moment you emit that from the framework will automatically do the shuffle sort grouping for you. It will do everything, and it will bring you the key, group by key, and the list of values. After that you can do whatever you want with the list of values, because now you have aggregated the data. You can do sum, do whatever you want with that, and then emit. In there you can emit however you want. Whatever you emit will come in the output file, and that logic can be as complex as you can.
So assume I want to find duplicate lines in a file. So how would that work?
Okay, so duplicate line in a file is a tricky thing. It's not very.
I can have duplicate lines within a mapper function, mapper block, the block which.
No, what you would do is, if you want to do a duplicate file function, I can give you a rudimentary solution for it. The solution will be, you will read every line in the mapper, and you will emit something called as the hash code of the line, okay, yes, as the key, okay, and the value will be nothing but the line itself, okay. The key will be the hash code, value will be the line itself. When it comes to the reducer, you will do by grouping by hash code. So you know that if the hash code has matched, that means the lines are same, and you would have got all duplicate lines together. But there is a slight possibility that those lines are not really duplicate, but the hash code has matched it together, but you will still get in the same reducer. And what you could do there is, you could put a logic to skim through the record and either split or make it similar. Okay.
Okay. I want to count the number of duplicate lines. Okay.
Yeah, number there, that counting you will have to do in the reducer. You will still do the same thing in the mapper. Yeah. Mapper is going to map and say give you a hash code, because for duplicate line you need to group by something, correct?
Yeah. So so the mapper takes key, and I mean the mapper should output key and value, right? So every time,
the key will be the hash code.
Yeah, but the value would be the number of times the line was encountered, right?
No, not required. You will put the line itself, because number of lines will not be proper, because you can do that. Okay, so one way is, you will say that I am assuming that there is no hash code conflicts. If you don't have hash code conflicts, you will say, okay, line number 1. Okay, I will say. Then you can count it. Okay, but if there is hash code conflicts, you cannot assume that 1 will work, because you will get an overstatement sometime. Got it, no? And you will not be able to also identify the line. If you want to identify the line and then do it, you will have to put the line in the value and get it, but the mapper will be very inefficient, because you are transferring large amount of data across the cluster.
If assume that first and third line are duplicates, okay. So the hash key for both the lines are same.
Correct. So it will get grouped.
I mean, the
and you will get both the line in the same record in the reducer.
Yeah, I mean, but both first and third line was processed by one mapper.
No, it doesn't matter, na, because the hash code logic is the same, na.
Yeah, I mean, hash code logic is same, but hash code logic is same, but the mapper which processed first and third line should say that this particular hash key I found it 3 times or 2 times, right?
No, no, it won't. It won't need to say. That is the way to think the mapper and reducer logic, because you are see, you need to look at it 2 things. Now, the moment you are trying to instigate state into the mapper, the whole logic goes for a toss. So mapper has to be purely record driven. Okay, it is taking a record and saying what is the hash code of it. I don't care whether it is duplicate or not. I am going to just generate a hash code for the line and either count the line or give the line itself to the reducer. Now it will come to the reducer. By the time all the hash code across all the mappers would have come. Okay, so now you are grouping by hash code. So anything which is similar will come together. Because if you try to introduce that logic in the mapper, then you are introducing state into the mapper, which is what our fundamental principle gets violated. Got it? Now this is how you have to start thinking about MapReduce.
Yeah, but what I still don't get is, but how would the output know that the first and third line are duplicates?
No, see, let's take an example. This is your example only. Let me get into the detail now. Okay, so let's say line is I am a boy. Okay, then second line is I am a girl. Third line is I am a boy again. Okay, so in the mapper you started calculating the hash code. I am a boy. Hash code is 20.
Okay.
You emitted 20. I am a boy as the output of the mapper. Second line, I am a girl. Okay, hash code 10. So 10, I am a girl output. Okay. Again, I am a boy. Hash code 20, I am a boy output. Now key is hash code. You group by key. So 20, 20 will go together. Okay. So what is the values in 20 and 20? I am a boy. I am a boy. So I am a boy will be a list. Got it?
So there will be 2 values to the reducer from this mapper, right?
Correct. And then it will group and it will have the key as the 20 and list of values will have I am a boy, comma I am a boy.
Okay. So what I thought is that if you think in terms of keys and value, whatever key that you whatever value that you associate with the key, the latest value would always be emitted. So no, but
no, it is not the latest value. All the values will come. It is grouping.
Yeah,
okay, and giving a list of value. It is not a single value. Remember, I'll go back because that's very important. You should know it. It should not be. It's a list of values. So remember here, list of values.
Okay.
And I have done that same thing here also. So you see, list of value 1, 1, 1.
I got it. I mean, I didn't.
Remember for others also. This is very, very important. It's a list of values, not value.